We're now going to take advantage of our idea of building general solutions from building blocks by taking a look at this differential equation and knowing that we've been given two different solutions here, or two proposed solutions. We're going to verify that they actually work, and then we're going to build our general solution after we verify that we've got building blocks that actually solve the equation. So the first step is just the verification. We're told that y1, which is e to the 2x cos of 3x, is a solution. Now, if we're trustworthy, we think that's great. I believe whoever told me, but we're not quite that trustworthy yet. So we're trusting that yet. So what we're going to do is verify by subbing in. And we're going to sub it right into this particular differential equation with the -4 and 13 you see there. Of course, we can sub in for the y, check, but we have to sub in for y prime. So that means we're going to need y prime, but fortunately, that's only a derivative away. We're going to use the product rule here. Derivative of the first would be 2e to the 2x. The derivative of the second is going to have a 3 pop out and a negative from the cos. Oops, cos of 3x. And because it's a second order differential equation, we're going to need y double prime as well. And for that, we just differentiate one more time. This is going to be a little longer, but it's still just a couple of couple of product rules. So we'll get another 2 out. And then the cos. Then the cos derivative will give us a 6, but it'll be negative times sine. And I just realized there's a little mistake here. The derivative of cos, of course, is negative sine, so that should be a sine there. So all of this part here came from the derivative of the first term. Then we can add on and say, there's -3. With the derivative of the first would be -6. E to the 2x, and keep the sign. And then second, we have a sine of 3x. We're going to get 3 times 3 is -9. E to the 2x, and then we'll have a cos this time, cos of 3x. And we can tidy that a little bit because there's cos and sine and sine. So what do we get? We're going to have 4 coses minus 9 coses is -5. Everything has an e to the 2x, so we'll keep it. And the sines, we have -6 and -6 will be -12. All right, so now we're actually in a position where we can sub in. And I should emphasize this is y1 prime. And now we're going to sub into our differential equation. The equation here is what we're going to put in. The left-hand side from that is equal to y double prime. That's this guy here. -5 e to the 2x cos, -12 e to the 2x and sine. Then -4 y primes. Y prime was up one line, here it is, 2 e to the 2x cos, and -3 e to the 2x sine. Try to make some room here. And last but not least, we're going to have 13 y's, and y was just e to the 2x times cos of 3x. All right. Now, rather than go to the next page, let's see if we can work this through. If we add up how many e to the 2x cos of 3x's we have, there are -5 of them, minus, what do we have here, -8 of them, plus 13 of them. Hey, -5, -8, plus 13 sounds an awful lot like 0. And we also have e to the 2x's with sines, with the 3x's as well. And that, well, we'd have 12 of them there, -12. And we would have -4 times -3 is positive 12. Hey, all of that is equal to 0, which is equal to the right-hand side. When we sub this y1 into the differential equation, calculate, simplify, cancel, it equals 0. And that's our verification that y1 is a solution. So y1, which is equal to e to the 2x cos of 3x, is, in fact, now it's a verified, confirmed solution. You'll see or notice at this point that these things are getting a little bit tedious. So we will simply say here, similarly, y2, which is the other partner of that, with sine of 3x, can also be shown to be a solution. Just by going through the same algebra. So nothing new there. You take the derivative and then the second derivative sub in, you'll find out, in fact, not surprisingly, that this cousin function here is also a solution. Now, once we've done that, we can simply build the general solution by putting them together. And here we're using the construction technique of y equals c1, y1 plus c2, y2, knowing that y1 and y2 are solutions. So we have two solutions, we're going to put them together, and in fact we can actually put values in here now. So anything times e to the 2x cos of 3x plus anything different if we wanted times e to the 2x sine of 3x would be the general solution. And again, this is to a very specific differential equation, one where we have the second derivative minus 4, the first derivative plus 13 of the function has to add up to 0 or cancel out to make 0. So that's a good starting point. We now have verification of building blocks. Once we have the building blocks, two solutions, we can add them and multiply them by something, and that'll be our general solution. Now sometimes we need something a little more specific. So all that being said, so this is all the same as before, we're going to add two conditions. We want the particular solution that satisfies not just the differential equation, but also goes through y equals 2 at time 0, and or x equals 0, and y prime equals -5 at the next point. And what we're doing here is using these to find the values of C1 and C2. So this is simply a matter of subbing in. We have our general solution, and from that general solution we have C1 e to the 2x cos of 3x plus C2 e to the 2x of sine of 3x. From that we can plug in y of 0 equals 5, sorry, y of 0 equals 2. And if we do that, we're going to get 2, that's the y value, equals C1 e to the 0, we'll do this first one explicitly, cos of 0 plus C2 e to the 0, sine of 0. And then we just remember our basic trig functions. Cos of 0 is 1, sine of 0 is 0, e to the 0 is 1, e to the 0 is 1. So at the end of the day, we just get 2 equals C1. Hey, that wasn't too bad. That gives us one of the constants for our solution. Now, if we're going to use the second point, we need to find C2. Fortunately, we have one other fact we can take advantage of, but it's going to be a little bit more complicated, of course, because this was our general solution. Let's put a big box around that. We use that again, but with the condition now that we need the first derivative equal to -5. Well, that means we have to find the first derivative of this, which is a whole lot of product rules, but it's still workable. Well, I think we'll do that on the next page. So we need y prime, which is equal to c1 y1 prime. Well, that'll be c1 times 2 e to the 2x. We've done these derivatives before, so we'll just plow through those. Derivative of the first times the second plus the derivative of the second, which would be sine, with the 3 popping out in the negative, plus the c2 times basically the same pattern, 2e to the 2x, sine of 3x, plus, and then the derivative of the sine part is just the positive 3, and then we get a cos. All right. And then we also have the condition that at y prime of 0 is equal to -5. Just confirm that. Y prime of 0 equals -5. Fantastic. And that's going to give us an implication that this derivative, -5, is going to equal this whole thing here with x equals 0 subbed in. Well, we're going to take a shortcut now that we've seen the pattern. Remember, coses of 0 are 1, cos of 0 is 1, sine of 0 is 0, sine of 0 is 0. We're going to get c1 times 2 times 1 times 1 plus -3 times 0 plus the c2, 2 times that's 0, e to the 2 times cos, that's just 1, so plus 3. So that guy disappears. And we get -5. Oh wait, we know what c1 is. c1 was equal to 2 from the last page. And so we get 2 times 2 is 4. You can just call it 4 there. Plus 3 c2s. Bring that over. -9 is 3 c2s. And c2 is equal to -3. So y equals c1 was 2. C1 went with the cosine function, e to the 2x cos 3x, and C2 went with the e to the 2x sine of 3x. And that's the particular solution, which also satisfies the specific, what we call initial conditions, y of 0 equals 2, y prime of 0 equals -5. So we can get much more specific if we knew the starting point and the starting velocity. If you think of y as position, then now we have a particular function that works and satisfies those particular instances. So it's a very common pattern to see the initial conditions helping us to solve for the C1 and the C2 from the initial conditions.